Welcome to this presentation on using machine learning to support repository review of LCF research outputs. The aim of this project was to explore whether machine learning could help research and knowledge exchange prioritize which records in a large elements export may have warranted human review, metadata enrichment, or repository follow-up. This sat within a real organizational need. RKE was dealing with a large volume of historical output records, and as REF 2029 preparation developed, there was value in being able to narrow a very large dataset into a more focused review workflow. Crucially, this project was not about asking a model to judge research quality. It was also not about letting a model decide what belonged in the UALRO. Instead, it was about using machine learning as a triage tool to help focus limited human time where it may have been most useful. In summary, this project tested whether machine learning could help RKE prioritize repository review across a large elements export containing 12,000 LCF research output records. Two models were compared, logistic regression and random forest. The core challenge became clear very early on. The target was highly imbalanced, with 11,903 records already deposited to UALRO and only 200 not deposited. That meant a model could have appeared highly accurate simply by predicting the majority class every time. Because of that, the project was reframed around identifying the minority class, records not deposited to UALRO. The final output was not just model metrics, it was a practical review workflow including threshold-based review lists and a post-model overlay using the existing best output flag. So the main conclusion was that machine learning was useful here as a human-in-the-loop triage tool. It did not make repository decisions or judge research quality, but it helped RKE know where to look first in preparation for REF 2029, thus creating high value. Business context mattered highly. The dataset came from LCF Elements Export, which contained historical records of research outputs, but not every record in Elements was automatically a problem if it was not in UALRO. UALRO was selective. It was intended to document knowledge with quality preferred to quantity. This boundary was supported by UALRO's own guidance, which describes UALRO as a permanent, publicly visible open access collection of individual research outputs, but it also stresses that it should not be treated as a full CV or activity log. The guidance states that items should constitute a documentation of knowledge and that quality is preferred to quantity. So right from the outset, the project had to avoid a simplistic assumption that every non-deposited record was an error. The real business challenge was that RKE needed to prepare and understand historical output data as REF 29 work developed. That meant knowing which records may have needed repository checking, metadata enrichment, or follow-up. But with over 12,000 records in the export, it would have been inefficient to review everything with the same level of attention. That was where this project fitted. The stakeholder objective was to support RKE with a prioritized review workflow, helping colleagues focus on the records most likely to need human review. The boundary was important, though. The model was not deciding what belonged in UALRO. It was not assessing research excellence. It was only supporting triage, so human RKE and repository judgment remained central. This project mattered because REF 2029 was one of the most significant external research assessment exercises facing UK universities. The Research Excellence Framework describes REF as the UK system for assessing research excellence in higher education, with outcomes used to inform the allocation of around £2 billion per year of public research funding. This made the quality and readiness of the underlying research output data strategically important, not just administratively useful. REF outcomes inform the allocation of block grant research funding, provided accountability for public investment in research, and gave evidence about the health and quality of research in UK higher education. So preparing this, the underlying research output data, was not just an admin task, but it was part of the evidence base that supported institutional research strategy. This project then aimed to improve RKE's confidence in that underlying evidence base that RKE may have relied on when preparing for REF. If records were hard to find, poorly described, inconsistently categorized, or unclear in their repository status, that created issues within our REF 29 submission. Methodology. The analytical question was, could machine learning identify metadata patterns associated with records not deposited to UALRO? The working hypothesis was that output type, status, date fields, and metadata completeness would all matter. In other words, the model might have learned that certain combinations of status, information, date patterns, and structured metadata were more associated with non-deposit than others. A simple rule or heuristic could certainly have flagged records already marked as not deposited, but that would only have told RKE what it already knew. It would not have combined multiple variables in a structured way, and it would have not created an adjustable review and prioritization mechanism across the whole export. That was where machine learning became suitable. Logistic regression was chosen for interpretability, and random forest was added as a more flexible ensemble comparison. This choice was supported by machine learning literature. Marloff's overview of logistic regression describes it as suitable for binary classification problems, which made it appropriate for this yes-no repository status target. Random forest was included as a comparison because Bryman's work describes it as an ensemble method that combines multiple decision trees, which can help capture more complex relationships between predictors. This slide shows the first major technical challenge in the project. The raw data set contained 12,103 records in 115 columns, so it was reasonably large and complex administrative data set. The original target variable was deposited to UALRO, which appeared simple at first because it was coded as yes or no. But once the target was inspected, it became clear that the dataset was highly imbalanced. Nearly 11,903 records were deposited to UALRO, while only 200 were not deposited. This became one of the most important methodological points of the project. If the model simply predicted that every record was deposited, it would have appeared highly accurate without being useful. So, and this is key, accuracy could not be treated as the main measure of success. This decision was supported by research on imbalanced classification, where accuracy are misleading because the model may appear successful while mainly predicting the majority class. Saito and Reismeyer argue that precision recall-based evaluation is more informative for imbalanced binary classifiers, which supported the focus of recall, precision, and threshold tuning in this project rather than accuracy. To make the task more relevant to the business problem, the target was reframed. Instead of trying to predict the majority class, the model focused on identifying the rare class, records not deposited, to UALRO. The preparation stage also included removing leakage fields, such as UALRO URLs and item status fields, because those would have directly or indirectly given the model the answer. Date fields were simplified into year features and missing flags, and metadata completeness features were created, such as whether a record had a DOI or publisher information. Finally, the data was split into training and test sets using stratification. This was important because there were so few not deposited records, so the rare class needed to be preserved in both parts of the split. This slide focuses on how the dataset was prepared in a way that kept the model defensible. The feature set started with structured metadata fields that could reasonably be connected to repository review patterns, such as output type, status, date fields, and metadata completeness. The key part of the preparation was removing data leakage. Data leakage happened when the model was accidentally given information that revealed the answer. In this case, some fields had to be removed because they were too directly connected to whether a record was deposited. There was also a moment of critical inspection later in the process. After the first model run, source UALRO appeared as a strong coefficient, meaning a strong indicator of repository status. That made sense, but it also raised a concern that the source field might have been indirectly revealing repository status. Source thus was removed. Importantly, removing source did not materially reduce performance. That gave more confidence that the final model was learning from a broader metadata patterns rather than relying on a near leakage field. The dataset was also cleaned by removing fields that could not help the model. Some were empty, some contained lots of very specific text values known as high cardinality fields, which could have made the model noisy rather than useful. Others had the same value for every record, known as zero variance fields, meaning they gave the model no way to tell one record from another. Basically, if a field did not help the model make a meaningful distinction, it was removed. This approach aligned with the government data quality framework, which emphasizes that organizations should understand, document, and improve data quality through proactive, evidence-based, and targeted work. In this project, that meant treating metadata preparation as part of the analytical method rather than as a background admin step. This slide shows the main model comparison. Logistic regression and random forest. LR was chosen because it was transparent and accessible by stakeholders alike. Random forest was used as a comparison model because it could capture more complex patterns in the data. The important point here was that overall accuracy was not the main success measure as mentioned previously. Because the dataset was so imbalanced, a model could get a high accuracy score simply by predicting that almost every record was deposited. That would look good on paper but would not be useful to RKE. So the evaluation focused on the not deposited class as mentioned previously. There were two important terms here before discussing the results seen in the visuals on screen. Recall meant how many of the not deposited records the model successfully found. Precision meant how often the model was right when it flagged something as not deposited. Looking at chart B then, the model comparison chart, LR had much stronger recall than RF, 0.625 compared with 0.350. LR thus found more of the rare records that RKE would actually want to check. The confusion matrix in chart C showed this more directly. In the test set, there were 14 not deposited records. LR identified 25 of them and missed 15. It also incorrectly flagged 533 records as not deposited, which showed why precision was low. This was why LR became the preferred model. It was not perfect and its precision was low, but for this use case, that was more acceptable than missing most of the records that may have needed review. So the conclusion here was that LR was the most useful model for broad RKE triage because it caught more of the rare records the data analyst was trying to surface. It was LR then that was used to create the list of records for review. This slide shows how the model can become more practical for real RKE use. The key idea here was threshold tuning. A threshold was simply the cutoff point where the model decided whether a record should be flagged. So if the threshold was set at 0.50, the model flagged records where it thought there was at least a 50% chance that the record belonged in the not deposited review group. This threshold could be changed depending on review capacity. This approach was supported by scikit-learn's guidance on decision threshold tuning, which explains that classification thresholds can be adjusted after training dependence on the metric or operational objective being prioritized. Looking at chart D, the threshold tuning chart, the main trade-off was clear. When the threshold was lower, the model found more of the not deposited records shown by the higher recall line, but precision stayed low, meaning more records were flagged even though they may not ultimately need action, known as false positives. Chart E related that to workload. At a 0.10 threshold, the model caught every not deposited record in the test set, but it created a massive review of 2,265 records, which was too broad for initial review. At 0.50, the model found 25 of 40 not deposited records and flagged 558 records. This was the broader triage option. At 0.70, it found 15 of 40, but the review list dropped to 93 records. This was smaller and a higher confidence option. Thus, the model gave RKE a controllable review mechanism. If the priority was wider coverage, the threshold could be lowered. If the priority was manageable workload, it could be raised. The final pipeline exported usable review lists, including a smaller review list at 0.70 threshold, a broader list at 0.50, and a highest priority list where a model score overlapped with the existing selector's best output field. Looking at chart F, the RKE review priority breakdown, the key category was the top one. 180 records were classed as highest priority. These are records where the model gave a high review score and the record was also marked as a potential best output. This was useful because it combined two types of evidence. The model gave an operational review signal while the best output flag added strategic context. Importantly, the best output flag was added after modeling, not used to train the model, so the model was not judging research quality. This aligned with trustworthy AI guidance, where human agency and oversight are treated as key requirements. In this project, that meant the model was designed to support RKE review, not replace repository or academic judgment. Chart G added the output type context. It showed that deposited plus best output overlap was strongest in articles and conference items, but also in exhibitions, book sections, art/design items, and books. For LCF, that mattered because research value was not only held in traditional written publications. Best outputs were important to review because they showcased LCF's excellence, which was important for REF 2029 and for sharing amongst the wider university research community to attract business to collaborate with LCF on income-generating research projects. The conclusion was that the model had been turned into a human review workflow. It helped RKE decide where to look first, while leaving repository decisions and research judgment with human experts. This final slide brings together the main limitations, future improvements, and final recommendations. The biggest limitation was the class imbalance. Only 200 records were not deposited to UALRO, so the model had a very small minority class to learn from. This was why accuracy was not treated as the main success measure. The second limitation was low precision. Precision meant how often the model was right when it flagged a record. In this project, low precision meant that many flagged records may not ultimately need action. However, this was acceptable only because the model was being used for triage. It was creating a review list, not making a final decision. The third limitation was specific to UALRO. Non-deposit did not automatically mean something was wrong. UALRO was selective and some records may correctly sit outside the repository. This was why the model had to support human judgment rather than replace it. So did the analysis succeed in meeting its intended goal? The data analyst would say yes, but in a specific and bounded way. The aim was to not build a model that decided what belonged in UALRO. The aim was to test whether machine learning could help RKE prioritize review across a large elements export. On that basis, the project did succeed. Logistic regression identified 25 of the 40 not deposited records in the test set, and the final pipeline produced practical review lists, including a smaller high confidence list, a broader review option, and a highest priority group where model score overlapped with the existing best output flag. There were also technical improvements that could have been made. The model should be validated with RKE and repository colleagues, tested on newer exports, and potentially refined for different output types. For example, practice-based outputs may need different review logic from journal articles or theses. The final recommendation was to use logistic regression as a human-in-the-loop triage tool. A higher threshold could be used first to create a manageable review sprint, while lower thresholds could be used later if RKE had capacity for broader review. Overall, the value of the project was not that machine learning decided what belonged in UALRO. The value was that it helped RKE know where to look first, reducing a very large element export into a more focused, explainable, and strategically useful review workflow, thus contributing to RKE's best possible submission to REF 2029.